Okay, so if we said we had a beat frequency of 6 hertz, and if we knew one of our two frequencies was 320, then we could find the other one. Because this equation right here that I have boxed says the other one has to be either 6 higher or 6 lower. So if it's 6 lower, it'll be 314, and if it's 6 higher, it'll be 326. Right now, we don't have a way of telling which one it is if all we know is one frequency and we know how many beats we hear. So this would be the case if you played two strings on two different guitars and maybe you heard 6 beats. And if you did, that means that they're out of tune by 6 beats. So if you knew one was exactly 320, then it meant the other person was playing a guitar that was tuned for 314 hertz or 326. And then you could adjust the tension to get them closer, and then you would play the strings again and you would see, did the number of beats go down? If it did, they're getting closer together. If it went up, it means they're moving further apart and you need to change the tension the other way. Okay, so our two equations, if you want to know the beats, you subtract the two frequencies. And if you know a beat in one of them, then you can take the beats away from the one you know and add it to the one you know to get the two possibilities of the second one. Okay, so this example, it just tells you two and it wants to know what's the beat frequency, subtract them. Interesting note, the human ear can only hear 7 hertz, beats of 7 hertz. If the two sounds are further than 7 hertz apart, we hear them as two separate sounds. They don't interfere for us. Okay, so we only get beats created if the two sounds are 7 or closer. In some of the questions, they're going to talk about a tuning fork. Okay, and this is what a tuning fork looks like. This particular one is 512 hertz. And tomorrow I will let you play with them a little so that you get to hear what they sound like. I have two different sizes, 512 and this one's 256. One of the things I'd like you to do for homework tonight is on page 431. 431, I'd like you to do question numbers 24 to 27. But question number 25 has an error in it. It tells you the two frequencies are 440 hertz and 437 hertz. Excuse me, it actually says 337, but it has to be 400 because otherwise they'd be 103 apart and you wouldn't hear any beats. So the 337 in question number 25 is really 437. Okay, so please do the questions on page 431, and it's numbers 24 to 27, and they're about beats. All right, one more thing we need to look at, and that is Doppler effect. Okay, and that's the 2 pages I asked you to skip there a minute ago to go to beats. So Doppler effect, I don't know that you've seen it, or I don't know if you've heard the word before, but you've certainly experienced it. If you've ever been standing outside when an ambulance and a fire truck goes by with their sirens on, you've probably noticed that the sound of the siren seems to change. It's higher pitch when it comes towards you and lower pitch when it goes away from you. So the Doppler effect is the change in the apparent frequency of the wave received. So the frequency isn't actually changing. It's because of the movement. Okay, so it's because of the relative motion between the source and the observer, developed by a guy named Christian Doppler. Okay, so if both the source and the observer are stationary, then you hear the frequency the source is making. If the source is approaching you, then you hear a higher frequency sound. And if you are approaching the source, it's the same. If you and the source are receding or going away from each other, then you hear a lower frequency sound. And probably the easiest way to explain it is with a picture. So at the top of the next sheet, I left you a space so you could draw a picture there. And if you had different colors, that would be good. So in the beginning, we're just going to draw a picture of what would it look like if the source wasn't moving. And so if the source isn't moving, then we would get nice, equally spaced circles. Right? So the source is giving out these waves. It's like you in the bathtub. Oh, we could have done this with the ripple tank maybe. Okay, so if the source is staying in the same spot, whether it's a fire truck or if it's ambulance, then all the circles, all the wavefronts will be the same distance apart. Okay? But what happens in the whoops, imagine that was the same distance. What happens in the Doppler effect is the source moves. And because the source moves, then it looks like the wavelength shifts. All right, so now we're going to go over here, and okay, so we're going to start with the bigger circle. So the source is originally here, and it sends out a wave, and it spreads out. So here it is. Okay, but in the next instant of time, the source isn't there anymore. It's moving. We're going to make the source move to the right. So it's now over here. So now this wave is slightly shifted to the right. Then it moves again to the right here. And so the wave is shifted again. And then it moves this color again to the right. Whoops. And so on one side, if I could draw this well, the waves would be getting closer together. And on this, so on this side, they're getting closer together. So if you were standing over here, you would hear a much higher frequency sound than if you were standing on this side. So here the source is approaching you. And so you're going to hear high frequency, short wavelength sound. Here the source is going away from you. So the wavefronts are going to be further apart. You're going to hear a lower frequency sound. Okay? And so from that we get an equation. We get two equations. We get F, which we hear, and we put this little dash on it to say that's the apparent frequency. And it's equal to the real frequency, brackets, V plus VO over V minus VI. And this is if you're approaching. So this is over here on this side, okay? So over here on this side, it's if the source and the person hearing the sound are approaching, okay? The V is the speed of sound. And I do not have this written on your notes, so you need to write it. The VO is the speed of the observer, the person hearing the sound. Actually, and I should probably not put sound, speed of wave, because it doesn't always have to be sound. It could be light. And this is the speed of the observer. And so O stands for observer. And then VS is the speed of the source. So S does not stand for sound, it stands for source. So V is the speed of the wave, in this case sound. VO, the speed of the observer. VS, the speed of the source. That's positive on the top if it's approaching, negative on the bottom if it's receding. Excuse me, negative on the bottom. So if it's approaching, positive on the top, negative on the bottom. If it's receding, it looks like exactly the same equation, except the positive and negatives are switched. So it's minus VO on the top, and it's plus VS on the bottom. And the way I usually tell people to remember is if you're lying on the sidewalk bleeding and the fire truck is approaching you, or the ambulance is approaching you, it's a positive thing. So positive if it's approaching the observer, okay? Or if it's an ice cream truck and it's approaching you, it's a positive thing. But if it's going away from you, then it's a negative thing. And so as long as you remember the sign on the top, the one on the bottom is different. Okay? So that's as far as I'm going to go today. Tomorrow we'll talk about it, we'll play with toys, and we'll do a bit more. Your homework, I dropped it. Your homework is on the sheet that says, towards the back, that says review. Okay, so you could do the sheet that says review, and if I could find it before the video runs out, there it is. Waves and sound review questions. So you could actually do all of these now, so you should try them so that tomorrow we'll know which ones are causing issues. So there's some beat ones here.